Good morning students and welcome to the session number 2 of Unit 17. This unit deals with pumps and pumping requirements, valves and appurtenances. In session 1 of this unit, we discussed what pumps are, what are the various objectives of this unit, what are the different types of services that are provided by the pumps, what are the different types of pumps, and we focused most of the session on centrifugal pumps. We also discussed the idea of the performance curves and the pumping efficiency. In today's session, we will be talking mainly about the reciprocating pumps, the four miscellaneous type of pumps that are commonly used in waterworks, what is boosting and how do we use booster pumps to increase either the pressure or the discharge coming out of a given network, and what are the various parameters which are used to determine the ideal pump for a given situation. So we will be discussing the selection criteria of pumps for waterworks. Let us start with what reciprocating pumps are. Reciprocating pumps convert mechanical energy into hydraulic energy by sucking the liquid into a cylinder in which a piston is reciprocating, which means that the piston is moving backward and forward. This reciprocating motion exerts a thrust on the liquid, and this increases the hydraulic energy or the pressure energy of the liquid, ultimately resulting a liquid with a much higher pressure energy than what it started off with. The key parts or components of a reciprocating pump are a cylinder with a piston rod, connecting rod, and a crank, the suction pipe, the delivery pipe, the suction valve, which is a one-way valve, and delivery valve, which is also a one-way valve. A one-way valve is a valve that does not allow water to flow in both the direction. The water will flow only in one direction, and hence it prevents any backflow from the system. We will be discussing more about the one-way valve into the third session of this unit. If you look at figure 17.19 from the e-content given to you, you can clearly see the key components of a single acting reciprocating pump, including the suction pipe, foot valve, sump, the delivery pipe, cylinder, piston rod, piston, as well as the crank. Reciprocating pumps can be classified on two different bases. The first classification can be on the basis of on how many sides does water come in contact with the piston. If the water comes in contact with only one side of the piston, then such reciprocating pumps are known as single acting reciprocating pump. If the water is available on both sides of the piston, then such pumps are known as double acting reciprocating pumps. The second classification of reciprocating pumps can be on the basis of the number of cylinders that are provided. Now, the number of cylinders that can be provided in a reciprocating pump can be 1, 2 or 3. Correspondingly, such reciprocating pumps are known as single cylinder pump, double cylinder pump, and triple cylinder pumps respectively. So we have discussed the two different types of classifications based on either the directions or the sides from which water comes in contact with the piston, and on the number of cylinders that are provided for classification of reciprocating pumps. There are a number of advantages and disadvantages offered by reciprocating pumps over the other pumps. One of the key advantages of a reciprocating pump is that it is very suitable in situations where a high and variable head is present. Such pumps are durable, they are flexible in operation, and they can provide us with a high efficiency provided there are no leakages from the system. Looking at the disadvantages of reciprocating pumps, one of the biggest disadvantages is that the initial installation cost is high. This increases the capital cost of the system. It is also not suitable for water that contains sediments, and hence reciprocating pumps cannot be used for muddy or turbid waters. In addition, the maintenance cost of the reciprocating pumps is high. So not only is the initial installation cost high, the maintenance cost is also very high for reciprocating pumps as compared to other pumps. So in general, based on these advantages and disadvantages, the reciprocating pumps are very commonly used in situations where high head is needed but discharges are low. Let us discuss about the rotary pumps. Rotary pumps are positive displacement pumps that use rotary motion instead of the reciprocating motion. Remember students, in case of reciprocating motion, a piston moves forward and backward. However, in case of rotary pumps, rotary motion takes place. Instead of forward and backward, it is a rotational motion. And this rotary motion is caused by either cams or gears. Rotary pumps has got low efficiency as compared to reciprocating pumps. For this reason, these are generally used for firefighting purposes because they are portable in nature, which means they can be carried around easily. Rotary pumps offer us a number of advantages. These are self-primed pumps, which means additional or external priming is not required. They can provide us with a constant flow. which means we can expect a uniform output from rotary pumps, and they operate at an RPM of 500 to 1400. Such pumps are very suitable for situations where the pumping space is limited, where we cannot have very large pumps, where a pump has to operate under high pressures, but the discharge is small. In those situations, rotary pumps are preferred over other pumps. In figure 17.21, schematics of rotary pumps are given, where you can clearly see that the rotating motion can be caused by either the cams or gears. Let us discuss the four miscellaneous pumps that are also used, other than the positive displacement pumps and rotodynamic pumps. These include jet pump, airlift pump, hydraulic ram, and submersible pumps. Let us first discuss the operating principle of a jet pump. In case of a jet pump, a stream of water or air is injected into the throat of a venturi nozzle. This leads to generation of low pressure, and this causes additional fluid to be drawn from an external source into this throat. If we look at the schematic of the jet pump in figure 17.22, you can clearly see the venturi tube, the nozzle, and you can see that there is a strainer provided into the system. The water from the pump enters the system, a low pressure or suction zone is created, which causes the suction of water from the well, and ultimately the output will include both the water that has been extracted from the well as well as the water that has entered from the nozzle. Small jet pumps are generally used for priming of centrifugal pumps. Jet pumps are capable of lifting water up to a height of 60 to 70 meters. These are compact and light. They are portable and easy to handle. One of the key disadvantages of a jet pump is that its efficiency is low as compared to other pumps. Let us discuss the airlift pumps. In case of airlift pumps, compressed air from the air pipe enters the educator pipe through a footpiece, and the combined mixture of air and water rises in the vertical educator pipe. In the schematic of airlift pumps, we can clearly see that the compressed air comes in from the air pipe, which has a very small diameter, as compared to an educator pipe whose diameter is much larger. The compressed air from the air pipe enters the educator pipe through an air diffuser, and this causes both the water from the sump as well as the air to rise up, and ultimately we get a mixed discharge consisting of water and air bubbles. There are a number of key advantages offered by airlift pumps. One of the first one is that airlift pumps are very useful for pumping waters that are either corrosive or gritty. The wear and corrosion in case of airlift pumps is small as compared to deep well turbine pumps. Airlift pumps are generally preferred for extracting large amounts of water from small boreholes. These are cheaper, reliable, and very simple in operation. When looking at the disadvantages of airlift pumps, one of the biggest disadvantages of an airlift pump is that it offers very low efficiency of operation. These are not suitable for raising water much above the ground surface, and they are less flexible in fulfilling the variable demands of water. So keeping in mind the various advantages and disadvantages of airlift pumps, we can determine in which situations such pumps can be utilized. Hydraulic ram are the third type of miscellaneous pumps that we are going to discuss in this session. Hydraulic rams are different from other pumps because they do not utilize any external power source. A hydraulic ram is an impulse type pump which raises the water by period application of force, which is suddenly applied and suddenly discontinued. In other words, hydraulic ram operates on the principle of water hammer. The flowing liquid is brought to rest, which increases the pressure due to the change in the momentum of the fluid. This pressure rise is then used to lift a portion of the water to higher levels. The key components of hydraulic ram are the supply tank, the delivery pipe, the supply valve, the air valve, and the delivery and the waste valves. We can see that the water from supply tank will enter into the valve box, air vessel will release air into it, and from there part of the pressure generated into the system will be used to lift the water to the delivery tank. The hydraulic ram are very useful for remote places where power supply is not available or dedicated power supply or continuous power supply is not available. These have negligible running cost and they require very little maintenance because they don't have a lot of moving parts. Submersible pumps are another type of miscellaneous pumps that we are going to discuss in this current unit. Submersible pumps are basically centrifugal pumps, and these are called submersible pumps because they are installed under the water. The pump is directly connected to an electric motor which is sited immediately below it, and the motor is capable of running under the water. Generally, the windings of this motor are surrounded by water from the well, and the water acts as a coolant and also as a bearing lubricant. Waterproof cables, which are clipped to the side of the rising main, they supply power to the motor. Submersible pumps can be easily and quickly installed, and they can be of smaller diameter. So we have discussed the four miscellaneous types of pumps other than the rotodynamic pumps and positive displacement pumps, including the hydraulic ram, the submersible pumps, the airlift pumps, and jet pumps. Let us look at boosting. Boosting is a pumping arrangement which increases the pressure or water quantity which is delivered through an existing main system. So we are, in layman terms, we are either increasing the pressure in the system or increasing the discharge from the system. There are three main boosting arrangements that are commonly used on need basis in an existing water supply system. These include addition of fixed extra flow to an existing supply, addition of a fixed extra pressure to an existing supply, and maintenance of a given pressure irrespective of the flow level. Now, addition of extra flow or pressure to an existing waterworks system is relatively easy. For example, if we need to double the flow or double the discharge, all that we need to do is we need to connect two similar pumps in parallel configuration. The pumps that are running in parallel configuration must have stable running characteristics so as to give us the desired amount of flow. Similarly, if we need to double the pressure, we need to connect two similar pumps in series configuration. The key aspects that one needs to understand or look for are that pumps that are running in series, the joint duty of these pumps should not overload the pump. In addition, any additional pressure that is generated because of this series configuration, it should not exceed the safe working pressure of individual pumps. Hence, by using a series or parallel combination of identical pumps or similar type of pumps, we can increase the flow and increase the pressure available in an existing water supply system. For any intermediate increase in flow or pressure, other than the doubling of pressure or doubling of flow, we can add a smaller pump in series or parallel configuration depending on whether we need to increase the flow or the pressure. The practitioners must remember one thing, that there would always be friction in the water supply network, whether small or large, and this friction in the system is going to cause results to be different from ideal situation or from what we normally expect. Figure 17.25 in the notes help us in determining the advantages offered by series and parallel configuration of pumps as compared to the operation of a single pump. A system characteristic curve S is also provided in this graph. This graph is drawn between water head measured in meters and delivery in MLD or million liters per day. When comparing a single pump with two pumps operating in series or parallel, we notice few key aspects. For example, when pumps are operating in series, the joint output head is less than the sum of individual outputs. Similarly, when pumps are operating in parallel configuration, the joint output delivery is less than the sum of individual outputs, which means in real life, even if we connect two pumps in series or two pumps in parallel, we do not expect the flow to exactly double or the pressure to exactly double. In such cases, we need to use the given curves of the pumps and determine what would be the best configuration and how much output or pressure head we can expect by operating pumps in series and parallel configuration. The third reason we use boosting or we use boosters is for maintaining a given pressure in the given waterworks system. A booster or a booster pump can be used to raise the pressure at the time of high draw off. This can be made possible by an automated system which is generally complicated in nature. Such a system will operate when the pressure reaches low value or the flow will reach a high value. Because of complicated automated arrangement, this is an expensive system and may also cause sudden pressure surge or sudden draw off in the existing water supply network. An alternative to such an automated system is provision of a balancing tower. A balancing tower can provide additional water during peak demand hours and will also help us in maintaining the pressure in the water distribution lines. Let us discuss the criteria that we use for selection of pumps for waterworks. In general, for most of our applications, the ideal pump or the most suitable pump is the horizontal centrifugal pump. This pump is generally applicable to most of the situations that we encounter in day-to-day life, except when large volumes of water is flowing under low heads or when we are pumping the water from wells, bore wells, or tube wells. Other than these situations, horizontal centrifugal pumps are the most suitable candidate for most of our pumping requirements. The advantages offered by such pumps include economy. Such pumps are cheap. They can pump large volumes of water with ease. The operation and maintenance is easy. Wide range of pumping requirements can be met through wide variety of designs that are available in the market. And hence, horizontal centrifugal pumps are one of the key candidates or one of the most suitable candidates for general applications. For wells and tube wells, we either use vertical spindle pumps or submersible pumps. Vertical spindle pumps are heavy duty pumps. They are capable of handling large outputs. They can provide variable speeds, which are necessary for pumping the water from wells or tube wells. On the other hand, submersible pumps are suitable for pumping large amounts of water against low heads. Vertical spindle motor driving a mixed flow pump with the pump submerged in water. For high lift pumping needs, fixed high speed horizontal multi-stage centrifugal pump is the most economical option that is available to us. When talking about a large pumping station, we need to install multiple pumps. Multiple pumps are provided for redundancy into the system or to act as a standby. Multiple pumps in a large pumping station will ensure that there is always adequate standby pumps available in case some pumps have a breakdown or they fail. This will also ensure that under any given conditions, we have full output that is needed for our ultimate use. Let us discuss the various parameters that are used or that are required for selection of pumps. These include the reliability of service, the promptness in service, what is the initial cost, which will help us determine the capital cost of the system, what is the efficiency of the pumps, are these low efficiency pumps or high efficiency pumps, what is the cost of energy that is required to run such pumps, what is the depreciation into such systems, the ease of maintenance and the maintenance cost including the depreciation, what is the ease of availability of spare parts and facility for repair, can the repair be done at site or do we need to remove the pump from the system and we need to take it a facility away from the point of installation. What is the running cost of the pump, including the operator cost as well as the labor cost? What are the capacities of the pumps? What is the suction head and the delivery head that are needed? How much quantity of water needs to be pumped? Is it a continuous supply or an intermittent supply? In a continuous supply, the water is available 24/7. In case of intermittent supply, the water is available only for a certain number of hours in a given day. What type of water needs to be pumped? Is it clean? Is it turbid? Is it muddy? Can it provide lubrication? Among others. Another parameter that we need to look for while selecting the pumps is the variation in the rate of pumping and the pumping heads. A key aspect while deciding the pumping mains is the determination of economic diameter of pumping mains. We need to reduce the size of the pumping main as much as possible to ensure that our system is economical and we can reduce the distribution cost of the water. If the provided size of our pumping main is less than the optimal size, we can expect significant frictional losses. On the other hand, if the provided size of the pumping mains is more than the optimal size, then the installation cost is higher and the system will not be as economical as it could have been had we used economic diameter. There is an empirical relationship that allows us to determine the most economical pumping diameter, pumping mains diameter. The equation is given as D is equal to 0.97 to 1.22 square root of Q. In this equation, D is the economical diameter measured in meters, while Q is the discharge measured in meter cube per second. This equation gives the optimal flow velocity between 0.8 meter per second to 1.35 meter per second. This brings us to the conclusion of session 2.